You ever sit in a waiting room, like maybe the dentist, and you're staring at the wall clock and you swear the second hand actually just stopped moving?
Oh, yeah. Time just completely
Right,
freezes.
it's agonizing. But obviously, that's just a trick of the mind. Today, though, we are diving into a clock where a single tick is so insanely fast that your brain, and honestly, even our current technology, can barely even comprehend it.
Yeah, we are talking about a massive leap here. We're moving from the era of microwave timekeeping into the era of visible light, specifically the Strontium-87 optical lattice clock.
Which sounds like something straight out of Star Trek. And the goal of our deep dive today isn't just to talk about making sure you aren't late for a meeting. We want to explore how these new instruments, which are like 100 times more accurate than our current global standard, are going to completely revolutionize everything from deep space navigation to literally mapping the planet itself.
Exactly. That's the real mission here. We are looking at a shift that actually turns timekeeping into a physical tool for discovery.
A tool for discovery. I love that. And speaking of tools for the future, I want to quickly mention our sponsor, Embersilk. If you are trying to streamline your business or even your personal life with AI, whether that's training automation integration or just figuring out where software agents can actually make an impact, you need to check out embersilk.com for all your AI needs.
So to really appreciate this leap in timekeeping, we have to look at the heartbeat of the clock. Right now, the global definition of a second is based on cesium atoms.
Right, the atomic clock standard.
Exactly. And those atoms oscillate at microwave frequencies, which is about 9 billion times a second.
Which already sounds incredibly fast.
It is fast. But strontium-87 ticks at optical frequencies, visible light. We are talking about 429 terahertz.
Wait, terahertz.
Yes, 429 trillion times a second.
Okay, so if cesium is like a ruler with inch markings, then strontium is a ruler with nanometer markings. We're just slicing time into way finer pieces.
That is a perfect way to visualize it.
Mm-hmm.
And to actually catch those ticks, scientists use an optical lattice. Picture an egg carton made entirely of laser light.
An egg carton of light, okay.
Right. And they use it to trap about 40,000 strontium atoms in this grid all at once.
Why 40,000 though? I mean, why not just isolate one atom and measure it really, really well?
Think of it like a crowded stadium. If you try to listen to one single person whispering the time, you might mishear them because of the background noise.
Yeah, that makes sense.
But if you have 40,000 people chanting it in perfect unison, the message is undeniable. Interrogating thousands of atoms at once instantly averages out the quantum noise.
Wow. And to keep them in that laser egg carton, I read they use a specific laser frequency called a magic wavelength, which is such a funny phrase for physicists to use. What makes it magic?
It's basically the Goldilocks zone. It's the exact color of laser light that traps the atom without disturbing its natural ticking rate. Usually they use infrared light at 813 nanometers. But researchers just recently discovered a new turquoise magic wavelength.
Turquoise, like the color.
Exactly. At roughly 497 nanometers.
Does the color actually matter, or is that just a neat trivia fact?
Oh, it changes the game entirely. This turquoise light interacts much more strongly with the atoms. So it creates deeper traps using significantly less power.
Oh, so it's way more efficient.
Exactly. And that efficiency is the missing link to taking these clocks out of giant sterile laboratories and shrinking them down for spacecraft or actual field work.
So we are looking at ultra-precise, portable timekeepers. What does this mean for the official second, like the literal definition of time?
It's due for an upgrade. The international governing body in Paris is actually planning to redefine the SI second around 2030.
Is strontium going to just take over as the solo standard then?
Probably not solo, no. The roadmap proposes a multi-species standard, so combining strontium-87 with other atoms like ytterbium-171.
Oh, I see, to build redundancy into the system.
Precisely. If one atom has a quirky reaction to a local magnetic field, the other species keeps the time honest.
How accurate are we actually talking here? Like, give me a real-world example.
We are reaching precision levels of 10 to the minus 18.
Okay, I'm going to need that in plain English.
Quintillionths of a second. Look at it this way. If you started one of these clocks at the Big Bang 13 billion years ago, it wouldn't have lost or gained even a single second by today.
That is absolutely mind-blowing. But if a clock is that insanely stable and it suddenly changes speed even a tiny bit, that implies something in the physical environment must have changed, right?
And that right there is the massive breakthrough. These aren't just clocks anymore, they are sensors. Einstein's general relativity tells us that gravity slows down time.
Right, the whole interstellar concept. Time runs faster at your head than at your feet because your feet are closer to the Earth's mass.
Exactly. Normally, that difference is way too small to measure on Earth. Not for strontium, though. These new clocks are so sensitive, they can detect the time dilation caused by a height difference of just 1 centimeter.
Wait, 1 centimeter? Are you saying if I move this clock from the desk to a coaster, you can measure the change in gravity?
Yes, you can. And this opens up an entirely new field called relativistic geodesy. Instead of relying on satellites to guess the Earth's shape, we can map the planet's gravitational potential simply by comparing clock speeds at different locations.
Like a quantum altimeter.
Exactly.
Hmm.
And it goes even deeper. Physicists hope to use this extreme sensitivity to bridge the gap between quantum mechanics and general relativity. We might actually be able to detect how gravity causes quantum states to break down or decohere.
That is just incredible. We're essentially building instruments that turn time itself into a map of the physical universe. It's so optimistic to think that just by measuring something as simple as a second better, we're unlocking a whole new era of human discovery and navigation.
It really is a beautiful next step for science. We're going to understand our universe so much better.
Well, if you enjoyed this deep dive into the incredible future of time, please subscribe to the show. And hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in, you guys.